Alrighty, friends, so let's take a look at concavity in this screencast. We're not going to talk about increasing and decreasing behavior. We're going to talk about concave up and concave down behavior, so we need a definition, and this is our working definition. The graph of a differentiable function, y equals f of x, is concave up on an interval if f prime of x is increasing on that interval, and f of x is concave down if f prime of x is decreasing. So the picture to imagine, you have some function that looks like this. In a very high school-y way, we would talk about concave up like a cup, concave up like a cup, and then concave down like a frown. We would talk about those kinds of high school-y things, up like a cup, down like a frown. It's very easy to remember that way. What is really happening? Through this interval where we are concave up like a cup, f prime is, oh that's red, terrible color coding job. F prime is increasing. F prime starts very negative, then it's not very negative, then it's 0, then it's a little positive, then it becomes very positive. So f prime values are going up from left to right. By contrast, if we take a look at the area where f is concave down like a frown, what does that mean? It means that f prime is decreasing. F prime starts very high, then it's kind of small, then it's practically 0, then it's a small negative number, then it's a large negative number. From left to right, f prime is decreasing. So let's put some things together from previous work. We know from our last lesson that if a function is increasing, its derivative is positive. So if f prime is increasing, f double prime is positive on that interval. And similarly, if f prime is decreasing, f double prime is negative. So this gives us a really easy way to know where a function is concave up or concave down. A little bit of vocabulary. A point where the graph of a function has a tangent line and where concavity changes is called a point of inflection. So if I were to go here and copy this and then bring it over here and paste it, we would say that this point here and this point here where concavity changed were called points of inflection, places where concavity changes. As a little side note, at an inflection point, either f double prime is 0 or f double prime does not exist. Those are two telltale signs that you could be dealing with an inflection point. And as an extra quick side note, f double prime could be 0 without there being an inflection point. The logic goes one way. At an inflection point, we expect f prime to be 0 or not to exist. But if f double prime is 0, that does not necessarily mean we're dealing with an inflection point, because we could take a look at the graph of x to the 4th, whose second derivative is 0 right there, but that is clearly not an inflection point. Okay? Okay. So, let's find intervals of increase or decrease and of concavity for f of x equals 1/4 x to the 4th minus 2x squared plus 4. Now, we could graph this function on our TI whatever and look for where the intervals of increase and decrease are. We could estimate where the intervals of a concavity are, but we don't have to estimate anything. We can take a derivative and, oh look, that cancels. Yay! And we get that, which factors very nicely. And so it turns out there are three critical points. Those are the associated x values. I've got a happy cubic, so we've got minus plus minus plus. And so what do I know? I know that f is increasing where? F is increasing where f prime is positive. Because f prime is positive. Similarly, f is decreasing in the other places. Why? Because f is decreasing where f prime is negative. But wait, there's more. F double prime of x. Well, that's sweet. And that means that on my f double prime chart, there are two places where f double prime could change sign. One is at 2 over radical 3, and the other is at negative 2 over radical 3. This is a happy parabola. And so what do I know? F is concave up on negative infinity to negative 2 over root 3 and 2 over root 3 to infinity. Why? F is concave up if f double prime is positive. And similarly, f is concave down between those because f double prime is negative. So if I ask you for intervals of concavity, second derivative, number line, look for where you are positive or negative. This brings us to the second derivative test for local extrema. Yes, I know, last time we looked at the first derivative test for local extrema and it involved the first derivative. This is the second derivative test for local extrema and it uses the second derivative. So, suppose f double prime is continuous on some open interval. If f prime is 0 and f double prime is negative, then f has a local max at C. Similarly, if f prime is 0 and f double prime is positive, then f has a local min. So, picture time, local max. What happens at a local max? At a local max, I've got a flat tan and I am concave down. So if I've got a flat tan, and I'm concave down, then I've got to have a local max. Similarly, local min. What happens at a local min? Flat tan and concave up. Flat tan and concave up. So if I get a flat tan where I'm concave up, I have a local min. But if f prime and f double prime are both 0, then we don't have this scenario, and we don't have that scenario. Neither a max nor a min. Hopefully that makes sense. I mean, it's one of those things that makes sense if you think about it. Okay? Okay. So, how does this pop up in some nasty question of death? Let's consider the function g where g prime is graphed. And I'm going to show you exactly what g prime looks like. G prime looks like this. Oh, that's a little, there we go. And then it goes through 1 and then down there and back up. This is the graph of G prime. Now, here's the curious thing. From a graph of G prime, I can know things about G. So, on the interval from -4 to 3, at what value or values of x does G have, and I can ask where G has a local max. I can ask where G has a local min. I can ask where G has an inflection point. Those are all things that I can ask. So in fact here, think this through with me. Two of those are really straightforward because we talked about them last time. Think for a moment, where does G have a local max based on what I can see from G prime? Where does G have a local min based on what I can see about G prime? Let's think about that and then hit the unpause button. Okay, so let's talk about a local max. Add a in fact, let's get a little bit of, oh, I can't break that up. Oh, that's terrible. Okay, so let's talk about that. At a local max, G prime changes from positive to negative. So G prime is positive, G prime is 0. G prime is positive, 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 negative. Right there. G has a max at x equals 1. G has a max at x equals 1 because G prime changes from positive to negative. If I'm interested in a local min, I'm interested where G prime changes from negative to positive because G changes from decreasing to increasing. And if I go from decreasing to increasing, that's a min. So is there any spot like that? No. Which brings us to inflection points. Inflection points are places where G double prime changes sign. G double prime changes sign. G double prime is the slopes of G prime. So G double prime is negative all through here because G prime is decreasing all through here. And then all of a sudden G prime is increasing again, so G double prime is positive. So there's an inflection point at x equals negative 3. Similarly, you'll see that there's an inflection point here where G prime goes from increasing to decreasing. And similarly over here, you'll notice that G prime is negative, G double 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 prime is positive. Wait a second, coach. What you're telling me is that the inflection points for G are where G prime has relative maxes and mins. Yes. In fact, we could ask, where is G concave up? Well, where is G concave up? G is concave up where G prime is positive, or if you like, where G prime is increasing. Where G double prime is positive, or where G prime is increasing. And that happens from negative 3 to negative 1, and from 2 to 3. This is different than when we looked at where G was increasing or decreasing. G is increasing where G prime is positive. And so there we'd just be looking at this area up to negative 3, not including negative 3, and then from negative 3 to 1. Those would be where G prime is positive, and so where G is increasing. So now all of a sudden we have a lot to keep track of. We have G, G prime, and G double prime, and they all matter. So you want to keep things straight. You want to recognize that, going back, if the function is concave up, its derivative is increasing, its second derivative is positive. And if the function is concave down, its derivative is decreasing, its second derivative is negative. Those are all things that you want to have straight in your mind. Awesome. Good enough. Your 15 minutes is set. Looking forward to seeing you in class. Thanks, everybody.